Welcome back to the Deep Dive. Today we're talking about a pretty uncomfortable truth in cybersecurity. You know that feeling when you lock your front door, you check it twice, and you just feel safe? In the digital world, that feeling is a complete lie.
It's a harsh way to put it, but you're not wrong. The old castle and moat strategy,
The perimeter defense.
Exactly. Where you build this big wall around your network and just assume everything inside is friendly. It's completely dead.
So, if the wall's down, what's next? We've got a whole stack of research here today, academic papers, industry reports from places like Cisco and Fidelis Security, some really dense stuff on encryption.
Right.
And it all seems to point to this idea that we need to stop trying to keep people out and just assume they're already in.
That is the core philosophy. Assume breach. The modern network is just too porous. I mean, you've got employees in coffee shops, data in the cloud, vendors logging in from who knows where.
There's no perimeter to secure.
There isn't a perimeter anymore.
Which brings us to this idea of the intelligent network. The whole pitch is that since we can't block everything, we need a surveillance system that's frankly smarter than we are. We're talking about machine learning models that watch traffic flowing through the pipes and spot the bad guys not by their face, but by how they walk.
That's a great analogy. It's all about behavioral analysis versus, simple identification. But before we get to the sci-fi stuff, the neural networks, we have to talk about architecture.
Okay.
Because you can have the smartest AI in the world, but if you leave the keys in the door, it doesn't really matter.
Right. Defense in depth. And the research starts with the basics. Access control. And this is way beyond just a strong password. It's MFA, multi-factor authentication, and RBAC.
But we need to be really specific here because everyone throws around the term MFA. The papers all say it's critical, right? Because credential theft is the #1 entry point. But this is a big...
But it's not a silver bullet?
It's not a silver bullet anymore.
Wait, I thought MFA was the gold standard. Something you know, something you have, something you are.
It is the standard, but attackers have evolved. We're seeing these MFA fatigue attacks.
Oh, where they just spam you with push notifications?
They just spam your phone with approval requests until you give up and hit yes just to make it stop. Or they'll do session token hijacking where they steal the digital cookie that proves you've already logged in.
So even if I scan my fingerprint, if they steal that cookie, they are me, as far as the network is concerned.
Precisely. And that's why assume breach is so important. You can't trust a user just because they logged in. You have to limit what they can touch. And that's RBAC.
Role-based access control. The principle of least privilege.
Right.
Meaning if I'm in marketing, I have no business accessing the engineering code base.
Exactly. It limits the blast radius. If your account gets compromised, the attacker is stuck in the marketing folder. They don't have the keys to the kingdom.
But that all sounds manageable in a traditional office. The IBM sources, though, they talk about this shift to modern infrastructure. Serverless computing, microservices. That sounds messy.
It gets exponentially harder there.
I wanted to ask about this because serverless sounds like a fake buzzword. I mean, there are still servers, right?
Oh, of course. There are always servers. But you don't manage them. In a traditional setup, you rent a server, install the OS, patch it, run your app. With serverless, like the IBM Cloud Code Engine they mentioned, you just write a function, a tiny snippet of code.
And the cloud provider does the rest.
The cloud provider spins up a container for the milliseconds it takes to run that code, and then poof, it vanishes.
So it's ephemeral. A ghost.
It is. And from a security perspective, that's a nightmare. You can't install an antivirus agent on a server that only exists for 200 milliseconds. You can't rely on static IP addresses.
So the perimeter is gone, the servers are ghosts, and the bad guys might already have my section cookie. This is the perfect setup for why humans just can't monitor this stuff anymore.
We can't. We just cannot cope with the volume or the speed. This is where machine learning stops being a nice-to-have and becomes non-negotiable.
Okay, but I want to push back on this AI is the savior idea for a second. We've had intrusion detection systems, IDS, for decades. Things like Snort. They use signatures. They work. Why overcomplicate it with neural nets?
That's a fair challenge, and Snort is fantastic. If you know what you're looking for. Signature-based detection works like a mugshot book.
If the face matches, you make the arrest.
Right. But what happens when the criminal gets plastic surgery? Or you get a completely new criminal who's never been photographed?
Those are the zero-day exploits.
Exactly. A signature-based system is always reactive. Someone has to be patient zero, get infected, get analyzed, and then a signature can be written. All that time, the damage is being done.
So machine learning isn't looking for a mugshot. It's looking for A weird walk.
It's looking for anomalies. The Fidelis security report really highlights this shift. You use what's called unsupervised learning to just watch the network and build a baseline. What does normal even look like?
Normal is marketing uploads big files to Dropbox on Fridays, but the engineering servers never, ever talk to the HR server.
Exactly. Once the ML learns that baseline, it can spot the deviations. So if an engineering server suddenly starts sending gigabytes of data to an IP address in a country you don't do business with at 3 a.m.,
It flags it.
it flags it. It doesn't know what the attack is, but it knows it's wrong.
Okay, that makes sense. But let's get into the weeds. How does this actually work? You can't just plug a neural network into a fiber optic cable. The data is just light and electricity.
This is the feature extraction problem. It's a huge part of the academic papers we looked at. You have to translate that raw network traffic into a language the machine can actually understand.
And that raw material is a PCAP, a packet capture.
Yes, tools like TCP dump or Wireshark grab the raw packets. But a packet it's heavy. It's got headers, payloads, routing info. If you tried to feed every bit from a corporate network into an ML model, you would melt the processors.
Too much noise, not enough signal.
Way too much noise, so you have to summarize it.
And the papers mentioned a few tools for this. Wireshark, Zeek, and Argus. What's the difference?
Think of Wireshark as a microscope. It gives you that deep packet-level view, layer 7. It can literally see the content of the web page you're loading.
Which is great for forensics after an attack.
Perfect for it, but it's way too slow and resource-heavy for real-time ML.
So what's the alternative?
You move up to flow-level analysis. That's tools like Argus or NetFlow. Instead of reading the letter inside the envelope, you just look at the outside.
The metadata.
Exactly. Who sent it? Where's it going? How big is it? How long did the conversation last?
And Zeek is somewhere in the middle.
Zeek is kind of the sweet spot. It's a favorite in the security community because it understands the state of a connection. It's not just counting packets. It knows this was a file transfer, this was a login attempt, without needing the full weight of the raw packet.
So we take this flow data from Zeek or Argus, and we turn it into, what, a spreadsheet?
Essentially, yes. We extract features, statistical data points, things like packet inter-arrival time.
The time between one packet and the next?
Right, or packet size variance. Is it a steady stream of equal size packets, like a video call? Or is it sporadic bursts of different sizes, like someone typing commands?
And that spreadsheet of numbers is what the ML model sees. It doesn't see hackers. It sees variance in column B is 400% higher than baseline.
You've got it. But now we hit the biggest hurdle in modern network analysis. The blind spot.
Encryption.
The encryption paradox.
Yeah.
We spent 20 years telling everyone to encrypt everything to protect their privacy. And it worked. Almost all traffic now is TLS encrypted.
So the attacker just wraps their malware in an encrypted tunnel. To the network monitor, it's just scrambled noise. Does the ML just give up?
You'd think so. But this is where the Cisco research on encrypted traffic analytics, or ETA, gets really fascinating.
How can you analyze something you can't read?
You look at the fingerprint of the behavior. Even if the payload is encrypted, the way the packets move tells a story. Remember those features? Inter-arrival time, packet size sequences.
Okay.
It turns out malware communicates differently than a human browsing Reddit.
So a botnet checking in with his command server has a different rhythm than me watching YouTube.
A distinctly different rhythm. And there's another dead giveaway in the handshake. When a secure connection starts, there's a client hello message. The client says, here are all the encryption methods I support.
And I'm guessing a normal Chrome browser supports a different list than some Python script a hacker wrote.
Exactly. The order of the cipher suites, the specific libraries used like OpenSSL versus a different one, it all creates a unique fingerprint. The ML can say, this traffic claims to be a normal user, but its handshake looks exactly like the TrickBot banking Trojan.
That is incredibly cool. It's like identifying a bank robber by the specific brand of shoes they're wearing under their disguise.
That's a perfect analogy.
Speaking of encryption, there was one other thing in the stack that felt a bit like magic. Homomorphic encryption.
Ah, yes. This is the real frontier. The problem with traditional encryption is that to do anything with the data, to search it, to analyze it, you have to decrypt it first.
And the second you decrypt it in memory, it's vulnerable.
Correct. Homomorphic encryption lets you do the math on the data while it is still encrypted. You can ask the database how many users are over age 30, and it does the math on the scrambled ciphertext and gives you back an encrypted answer. The data is never exposed on the server.
If that's possible, why isn't everyone doing it?
Because it is incredibly, unbelievably computationally heavy. Orders of magnitude slower than normal processing. It's getting better, but it's not ready for prime time across the board yet.
Got it. So it's the future, but the future's expensive. Let's pivot back to what ML is catching right now. The research really focused on two big categories: DDoS and pivoting.
Let's start with DDoS. Distributed denial of service. Most people think of it as just flooding a website until it crashes, but from a detection standpoint, it's tricky.
Because a DDoS attack can look a lot like a legitimate flash crowd, right? If you launch a new product and 1 million people show up, that's good. If 1 million bots show up, that's bad.
And the neural network has to tell the difference. The paper on this cited over 99% accuracy in classifying specific flood types, like a SYN flood.
Remind us what a SYN flood is.
It's an exploit of the TCP handshake. An attacker sends a SYN packet, which is like saying, "Hello, I'd like to talk." The server replies, "Okay, I'm listening," and sets aside some memory for the conversation.
But the attacker never replies.
Never. They just leave the server hanging. Do that 1 million times, the server runs out of memory. It's like ordering 1,000 pizzas and never opening the door.
And the neural net can spot that. It sees a massive spike in half-open connections that doesn't look like normal traffic.
Instantly. Okay, so that's the noisy stuff. What about the quiet stuff? Pivoting.
Lateral movement.
This is the silent killer. An attacker compromises a low-level machine, the receptionist's iPad, and uses it as a launch pad to get to the internal database server.
Because the database won't talk to the internet, but it will talk to the receptionist's iPad.
Right. To the internal firewall, it looks like a trusted connection. The paper suggests using something called PCA principal component analysis to spot this by looking for correlations in the traffic flow.
How does that work?
Well, if the receptionist's iPad suddenly gets a connection from some... Exactly. A normal iPad doesn't behave like a router. The ML spots that weird correlation source A to B, then B immediately to C, and it flags it as suspicious.
And this really gets at the difference between passive and active attacks.
For sure. The research is clear on this. Passive is reconnaissance. Port scanning, mapping the network. The attacker is just watching. Active is when they actually start doing things, launching the DOS, spoofing identities, modifying data.
And the goal of this whole intelligent network is to catch them at the passive stage.
You want to catch the burglar while they're casing the house, not after they've emptied the safe.
So we built this picture, a layered defense. You have the architecture, the access controls, and this big ML brain on top of it all, analyzing flow data, even encrypted traffic. It sounds pretty comprehensive.
It is, but I have to add one major word of caution. The human element.
Alert fatigue.
Exactly. If you tune your ML model to be too sensitive, it will flag every shadow as a monster. And if your security team gets 5,000 alerts a day and 4,990 of them are false positives,
They'll just start ignoring them or turn it off.
and they'll miss the one real attack hidden in all that noise. So the quality of the data you train the model on is paramount. Garbage in, garbage out.
It really feels like an arms race. We build a better wall, they build a better ladder, we build AI surveillance, they read.
Yeah.
Well, what do they do?
That's the final thought I really want to leave you with. We are using ML to defend, but the attackers are starting to use ML to attack.
Adversarial AI.
Yeah. Imagine an AI that can scan your network for vulnerabilities faster than any human team. Or an AI that can write phishing emails so perfectly personalized that no spam filter can touch them. Or, and this is the really scary part, an AI that learns how our AI works and generates traffic specifically designed to fool our detection models.
So the attacker's AI figures out exactly how to walk so that our AI thinks it's a friend.
Exactly right.
Yeah.
We're moving to a future where it's just algorithms fighting algorithms. If the offense is automated and the defense is automated, where does that leave the human analyst?
Hopefully not just watching the scoreboard.
Hopefully. It means the human role has to shift from watching screens to designing the logic and making those high-level strategic calls.
Well, on that slightly terrifying but also fascinating note, we'll wrap up. The castle walls are down, the network is invisible, and the robots are fighting in the background.
Just another Tuesday in cybersecurity.
Thanks for listening to this deep dive into the intelligent network. Check your passwords, maybe enable that MFA, and we'll see you next time.